So welcome everybody to today's special year seminar on theoretical machine learning at the Institute for Advanced Study. Today we are delighted to have Professor Inderjit Dhillon as our speaker. Inderjit is the Gottesman Family Centennial Professor at UT Austin and an Amazon Fellow. He is best known for his extensive contributions to optimization on matrices, clustering, and numerical linear algebra, and has also made a broad array of contributions to sparse recovery, distributed optimization, adversarial robustness, statistical learning theory, and the theory of deep learning. Inderjit is a fellow of the ACM, IEEE, SIAM, and the AAAS, and is the recipient of the ICES Distinguished Research Award, the SIAM Outstanding Paper Prize, and the SIAM Linear Algebra Prize. Additionally, he served on the editorial boards of the Journal of Machine Learning Research, the IEEE Transactions on Pattern Analysis and Machine Intelligence, Foundations and Trends in Machine Learning, and the SIAM Journal for Matrix Analysis and Applications. Today, Inderjit will tell us about multi-output prediction, theory, and practice. Please welcome Inderjit Dhillon.
Okay, well, thank you for the nice and kind introduction. It's a pleasure to be giving a talk today at the Institute for Advanced Studies. Of course, I would have loved to be in Princeton, but I've been giving a lot of pre-recorded talks. So in a way, I actually welcome that I'm giving a live talk. It's a lot more natural. So let me, I've shared the screen. So this has actually been quite a favorite topic of mine for the past 6 or 7 years. So today I'll talk about multi-output prediction. The first part of the talk, I'll talk about both methods and associated theory. And then I'll actually pivot to talking about real practice and making it scalable for, making these methods scalable for real-time applications. So let's see. Okay, so here's the outline of my talk. I'll first introduce what I mean about multi-output prediction. I'll outline the challenges. I will then talk about a few of these methods. And how they meet the challenges, inductive matrix completion, and talk about a framing of a problem called positive unlabeled learning that comes from one of the challenges that I outline. And then towards the last maybe 25 minutes of my talk, I will pivot to really talking about the practice, where I'll talk about some more recent work we've been doing for these multiple output prediction problem. And that project is called PECOS, which stands for Prediction for Enormous and Correlated Output Spaces. And then I will conclude. So, you know, when we look at, an introductory course in machine learning, then these are some of the toy problems that we kind of mention, or problems that we mention. For example, on the bottom right, you have regression of a variable to be predicted on one or more dependent variable, but there's exactly one output variable. And then in classification, we may want to predict whether an email is spam or not. Again, exactly one output variable. Or we have some small number of possible outputs, right? So for example, in digit recognition, we may want to predict whether a digit is 0 through 9. So in this case, the size of the output space is 10. But in many modern problems, you have many, many outputs, possibly in the millions. So here is an example. This is Wikipedia tag recommendation. So over here, I show a Wikipedia page. This page happens to be on machine learning. And on the bottom right, you may not be able to see it, so I have repeated it to the left, are the categories that are associated or given by, I think in this case, humans, for these articles. So in this case, the 4 categories are learning and computer vision, machine learning itself, learning, and cybernetics. And so if we look at the collection of Wikipedia pages, and now we want to think of each of these tags as a label, then we can have millions of labels or millions of possible outputs. And the problem is, given, let's say, a new machine learning, a new Wikipedia page, can you automatically assign tags or labels to this problem, or expand on the set of tags already given to a particular Wikipedia page? These problems are also there in advertising, where we may want to do keyword recommendation for a website. They occur in many domains. This is an interesting problem that I worked with a colleague of mine at UT. The problem is to predict genes that might be associated with a given disease or a phenotype. And I will go into more detail into this application a little bit later. Okay, so like I said, if I open up textbooks, you're typically given somewhat toy problems. And this is the first, this is the textbook on elements of statistical learning by Hastie, Tibshirani, and Friedman. And out here, I've given the table of contents for chapters 3 and 4. So if you look, chapter 3 is linear methods for regression. Chapter 4, linear methods for classification. And most of the material in these chapters is about the single output case, except there are, about a small section, subsection, I think it's around 2-3 pages in this book on multiple outputs. Similarly, if you look at the textbook, machine learning textbook by Chris Bishop, I think they appeared around they were published around the same time, and very similar, right? So chapter 3, linear methods for regression, chapter 4, linear methods for classification. And again, most of the treatment is about the single output case, but there is a small subsection for multiple outputs. And if you look below, there's also, multiple classes, but generally the number of classes is pretty small. So so today, of course, I will talk about multi-output prediction motivated by some of the modern prediction problems that I talked about. For example, Wikipedia tag recommendation. So let me set the stage. So I will be using this kind of picture quite a lot. So the scenario is that we have training data, which is assembled in a training data matrix. So the ith row of this matrix is the ith training data with D features. And then instead of having just one output variable, I have 1 through M output variables, and I will assemble them in this target matrix of Y. And then if I just start from very simple methods, I can think of trying to do, let's say, linear regression for these outputs. So now instead of having the case of just one output variable, there would be one coefficient vector. Now there is a coefficient matrix which has the same number of columns as the number of outputs. And what I want to try and do in training is say that X times W, which is like have a simple, let's say, a linear method or a linear model, XW is nearly equal to Y. And if I assume the outputs are independent, then I can just decompose this problem. This is the optimization formulation, and F denotes the Frobenius norm. It's well known that this problem has a closed form solution. And over here, I've just given the closed form solution in terms of the SVD, although the SVD or the singular value decomposition of the training data matrix is not necessarily required for solving this problem. So, very simple elementary. And if I now look at the case of classification, I can do something similar. Of course, it won't be in general closed form, and you can do, let's say, support vector machines with a hinge loss or logistic regression for each of the labels or each of the classes. And sometimes this is known as binary relevance, which refers to independent binary classifiers for each label. And each of these classifiers might be one versus the rest, or one versus all. So for the scale of problems that we are interested in, let's do like a back of the envelope calculation. So let's consider a small subset of Wikipedia. So this is a Wikipedia data set that is available in the public domain, pre-processed and so on. Has about 500,000 labels. So, fairly large output size, but for some of the problems that occur in industry, it's actually could be fairly small. The number in this example, let's suppose we have 1.5 million Wikipedia training documents. And like I said, L is the number of labels or the output size, and that's 500,000 or 500,000. And suppose that the average document length is about 1,000. Okay, so this is a text document. So the features can be constructed through the words that are contained in the document. So you can use a traditional way of converting each of these Wikipedia articles to a vector. This is what I refer to as a TF-IDF vectorizer. And in this case, the total vocabulary, the number of distinct words with probably some thresholding in these 500,000 Wikipedia articles, 500,000 Wikipedia labels and 1.5 million Wikipedia articles is about 2.5 million. So this is the setting in this problem. Of course, one thing I will make you aware is that each of these training data is very sparse, right? Because the average document length is only about 1,000. Now, suppose that we take the approach that I had outlined in the previous slide, right? Binary relevance, independent binary classifier for each label. Then we can make a reasonable assumption, software such as, we've tried software such as liblinear and so on, which is extremely efficient. Each classifier on a document length of about 1,000, where the vocabulary size or the feature size is 2.5 million, you can train in 50 seconds. And if we assume that, then the overall training time would really be very prohibitive on one CPU. And even if we assume like full parallelization, let's say on a 16-way computer, it would take nearly 2 months to just have to do one training on this data set. And not only is the training time prohibitive, but even the memory requirements are prohibitive, right? Because now we have to store a coefficient vector for each of these 500,000 labels. And so this requires terabytes of disk usage. And now if you were also to take sort of a modern deep learning approach and try and train these multi-class classifiers using a simple softmax over the L labels, where L would be 500,000, then the overall training time would actually be much worse, could be worse than given above. And the memory footprint is still quite expensive. So, you do this back of the envelope calculation and you realize, hey, that naive approaches are really prohibitively expensive, especially because we want to be able to scale to label sizes which are in the millions, maybe even tens of millions, maybe even the hundreds of millions. Okay, so these are some of the challenges that one encounters in multi-output prediction. So here I have listed the challenges that I will talk about. So, large number of outputs, but the outputs are usually correlated and they may have missing values. typically when you talk about prediction problems, regression problems, the target variable, or sorry, the target variable or the target class generally doesn't have features. But like if you think about the Wikipedia tag recommendation problem, it is actually made of words, so the outputs themselves have features. Many times you only have positive labels associated with the data, and so there is this kind of problem has been called positive unlabeled learning. So let me spend the first half of the talk talking about these three challenges and how to try and overcome them. So let's look at the first one, which is large number of correlated outputs. Okay, so we'll actually just talk about that for the time being without thinking about missing values. So one way to try and model this would be to look at, to model the coefficient matrix as being low rank. So here I've given the same kind of picture as above. X times W is nearly equal to Y. So a fairly simple linear model, except now we believe that the outputs are correlated. So we will model the coefficient matrix as a low rank matrix, say of rank K. Right? So this is not really new. Reduced rank regression has been around for a while. Eisenman wrote a paper in 1975, and Bryman and Friedman wrote a paper where they had a method called Kurtz and Way in, I think, around 97. And I think it's briefly mentioned in their textbook. So, it's been around for a while. Here on the right-hand side, I've actually included a kind of a more modern look at this kind of problem so that we can make a connection with neural networks. So I can write this as, here are the features over here. If this matrix is W1, then this is W1. And we get an intermediate layer that is W1 times Xi. Now, my target variable over here, I haven't assumed it has features. So I have one hot encoding over here. And so if I turn on the jth to do a prediction for the jth output, I can turn that bit on and I get W2 times EJ. And then the final prediction is this inner product between these embeddings, if I may call them. But it's basically the same thing over here expressed in this picture. And of course, right now, we are not considering any activations over here. They're just linear. So if I actually go through, this particular problem, reduced rank regression, you formulate the problem. It is a low rank optimization problem, right? But through the wonders of the singular value decomposition or the SVD, it turns out that there is a closed form solution for this problem, right? And so, but there's nothing new. This has been known for a while. If I come back to the Wikipedia prediction problem, if you just look at the tags associated with this machine learning Wikipedia page, learning in computer vision, machine learning, learning cybernetics, first is you might say, hey, some of these are a little bit noisy. And then there seem to be some missing values, right? So for example, statistics could be something which it could be tagged with, maybe data mining, data analysis, data science. So they're typically, these applications, there are lots and lots of missing values. So as a result, our picture now turns over here where I have X is the training data. And then on the target side, I have Y over here, which now has many, many missing values, right? So these question marks denote missing values. And this picture is a little bit misleading because, M can be, in the hundreds of thousands, millions, and typically as you get more and more outputs in the kinds of problems that I'm talking about, the percentage of missing values is extremely high. So it's maybe that more than 99% of these target values are actually missing. So we can posit a low rank model to handle correlations and missing values. So I can get similar picture as before, where W is expressed as a low rank matrix and explicitly factored into a rank K matrix over here. And then I can formulate the objective very similarly to what I had before. So there is really not that much difference. Over here, I had the minimization over rank up to rank K matrices, coefficient matrices W was all over all the entries of Y. That's what this Frobenius norm denotes. Whereas over here, now I have only the known values. So if I denote the number, the set of observed outputs by omega, then this optimization problem is only over omega. And now we actually don't have any closed form solution for this problem. And this has, as I will very quickly point out, this has relationships to the matrix completion problem, but this problem is in an inductive setting, right? That we may want to be able to predict for a new input. Whereas matrix completion is the problem of predicting for existing rows and columns of the matrix. So there is no closed form solution, but again, inspired by the matrix, even though the problem is different, inspired by the matrix completion literature, one can do a convex relaxation of this problem. So this is the trace norm or the nuclear norm constrained optimization problem. Again, the objective is over the IJ pairs that are observed. So this algorithm 1 uses convex relaxation. Algorithm 2, I can explicitly factor W into its low rank components, W1, W2 transpose, each of which is rank K, okay? So I'm assuming here that Xi, the training data or the inputs are d-dimensional, and then I have rank K and I have M outputs. So I can formulate this alternating least squares problem with a particular regularization. And of course, when you solve this in an alternating manner, each of the subproblems become convex, or rather in this case, quadratic. It is generally computationally cheaper than the nuclear norm method. And both these methods actually work reasonably well in practice. So like I said, I've been interested in this problem for quite a while. So this is the work that I did 6 years ago, probably initiated it about 7 years ago. Incidentally, when I was visiting my ex-student Pratik Jain at Microsoft Research in Bangalore. That's when I started working on this problem. So that's how, that's one way to meet the first challenge. And then the second is that, hey, the outputs may also have features. So in this case, we call this problem as inductive matrix completion. So again, if I take you back to the Wikipedia problem, it's not that just that the inputs or the Wikipedia page has features, but the tags themselves are words or phrases. And so the tags themselves have features. And in many other applications, the outputs may have features. So this we refer to as the problem of inductive matrix completion. And in this case, again, to repeat, not just the fact that the inputs are features, but each of these M outputs, in particular the jth output, has Zj as a feature. And sometimes they actually can be in the same dimensionality. Sometimes they may be in different dimensionalities. For ease of exposition right now, we'll just assume that they are both in the same high dimension or same dimensionality. So now what you want to try and do is you may actually want to do prediction for not only a new input, but also possibly a new output, right? And so what you want to do is you need to try and model these pairwise interactions between the input features and the output features. And the natural way to do is to move from linear models to bilinear models, and they'll individually be linear in the input features and linear in the output features. So this is now my picture that I've been kind of carrying through. Right now, let's not assume that there are any missing values. Let's assume that all the values here are known, but these are the output features and these are the input features. And if you again formulate the problem, it turns out that well, if you don't have a low rank, if you don't have a low rank constraint, you can again solve the problem in closed form. But even when you have a low rank constraint on the coefficient matrix, then you can actually get a closed form solution through the singular value decomposition of, in this case, not just the input feature matrix, but also the output feature matrix. In practice, when we come to this problem, we are back in the same setting where the outputs also have missing values. So when the outputs have missing values, then we can formulate the problem in a very similar manner, right? So now I have both xi as input features, zj as output features. And now my model is yij minus xi transpose w zj, right? Earlier this was ej when, or the jth column of the identity when there was no feature associated with the output. Again, I can have two very similar algorithms, convex relaxation, and I can then also do, so this is using the trace norm minimization, and this is using sort of alternating least squares. And now you guys, all of you might be thinking that, hey, this is has similarity with the matrix completion problem. And so are there guarantees for recovering the ground truth or recovering the model? And then, of course, the question is, how many observations does one need, right? How many observations omega suffice, and what is the structure maybe of those observations so that I can actually have guarantees for recovering the model. So like I said, the parallel is with the traditional matrix completion problem where, for example, you may have users as rows, movies as columns, and you only partially observe some entries. And over here, I've actually shown you again the neural network picture. There are no features associated with the rows and the columns, so it's just one hot encoding of the which captures that this is the ith row and this is the jth column. And then in seminal work, Candace and Recht showed in 2009 that you only need to get order tilde, which hides polylogarithmic terms, order tilde kn entries, right? K being the rank over here, and n being the number of, let's say, users and movies. So that is recapping traditional matrix completion literature, but now in this inductive matrix completion problem, remember that the degrees of freedom are not actually proportional to n. So n is the number of rows, and for simplicity, we'll assume that it's the same as the number of columns, right? But the features are in d-dimensional space. So the coefficient matrix, the size of this coefficient matrix is d times k, and then because it's a low rank matrix, it's 2 times dk. So the degrees of freedom are order kd. So the question is, can we get better sample complexity than linear in the in n, which may be the number of users and or the number of movies. Okay. So again, just as a parallel, I've included this picture, which shows that it is, you can think of it as a neural network, of course, without any non-linearities. So the answer to this question is yes, we can get better sample complexity. And we showed this in a 2015 paper where we showed that in this problem, when the dimensionality is D, then you actually need to observe about k times d log d entries in the matrix, and then you can get exact recovery. Of course, we have the standard kind of conditions that accompany matrix completion, which are that they have to satisfy incoherence conditions. Similarly, for alternating least squares algorithm, we can actually also get corresponding guarantees, which essentially transfer over from the matrix completion literature, right? So we can show that for inductive matrix completion, the complexity only depends on D. So in practice, just realize that it can actually make a huge difference, right? Because your number of users and number of movies might be very large, but suppose you have a low dimensional representation, or the features D might be only, let's say, so the number of users might be in the millions, number of movies might be in the millions, but your feature for each user, let's suppose, is only in the thousands. So now this says that with much fewer observations, you can actually do exact recovery.
So we have a question from the audience on, I guess, the convex relaxation portion of the guarantee. So the question is from Devda Dubashi. The question is the log-in factor necessary?
In our results, we do see them. So I don't believe there's been follow-up work that reduces that.
Thank you. And okay, so we have a follow-up question. So non-convex optimization usually just goes to a local min, but are you claiming a global optimum here?
Oh yeah, this is, yes. So this is, when you have these conditions, then this theorem says that, after H iterations of ALS, then this is going down. So this is the exact recovery setting, right? Suppose I have that Y comes from a particular model, right? So Y, the ground truth Y is X W star Z transpose. And the question is, with this algorithm, can I exactly recover W star? And what we are saying is for any epsilon, we can actually recover because the alternating least squares algorithm kind of decreases the error at each iteration through this alternating minimization step. If you look at the proof closely, it very much actually resembles like a power iteration kind of scheme.
Thank you. And another follow-up question. So do you need a special initialization for the non-convex optimization?
Look, in practice, I think for this case, we don't, but I will, there are, in the nonlinear case, which I will get to, is we do need some initialization with tensor methods. In this case, I actually now don't recall, but I will, it's been a while, so, but I don't think you need that, but I'm not sure. Okay, we can look at this paper in detail.
Okay, thank you.
Okay. Okay, So now the question is, all this is talked about linear inductive matrix completion. And so, if I look at some literature which has been in, the practice of deep learning. So this is a paper in 2013 saying, learning deep structured semantic models for web search. So this is a deep structured semantic model. It's called the DSSM model. So if you look at it closely, it's actually nothing but a nonlinear inductive matrix completion method in the terminology that I've used. So in this case, you can think of queries as the inputs, documents as the outputs. Here you have like, multiple layers as in a multi-layer perceptron, and multiple layers over here. You get low dimensional embeddings at the end, and then from the final layer, you may compute, let's say, either a cosine measure or an inner product to give the relevance of the document D. Oh, sorry. Oh, okay. Okay, I think this is good. Sorry, to get the relevance of query Q with document D. And if you look at it, I mean, it's actually just inductive matrix completion method. Of course, there are non-linearities over here. So the question is, can you actually give any guarantees on this nonlinear inductive matrix completion problem? So what we did last year in NeurIPS was analyzed a much simpler variant of this problem that just has one hidden layer. Okay? So if you look at linear, if I again make a parallel with, for example, this picture over here, there was no nonlinearity. Now, what I've done is, of course, over here, there are nonlinearities at each intermediate step. And now what we can do is we can have, take a simple case, the simplest case, which is have a nonlinearity have only one hidden layer and look at the nonlinearity over there. Okay? So now the inner product is not just between W1 transpose Xi, but W1 transpose Xi, where there's an activation function on this particular vector. So if I now look at this problem and I do look at this optimization problem similarly as before, I can get this objective function, right? Where now Ij belongs to the values observations omega, but now I have this nonlinearity. So the question is, in this is the simplest setting in some sense. In this setting, can we actually extend the results? So this is mainly the work of my student Kai Zong, who did it in 2 steps. So in 2017, what we did was we analyzed one hidden layer, multi-layer, just one hidden layer neural network. So in that case, what we had is just sort of the left side of this picture, and then a final layer to give the output. And in that case, we were able to give recovery guarantees. And then last year, we were able to extend that. It is more complicated because now, if I may use the term, it is bi-nonlinear, right? So there's a nonlinearity here, there's a nonlinearity here, and then you kind of mix them together by taking this inner product. And so Kai Zong was able to show that for this simple set, for this, well, simple in terms of the practice of neural networks, but does lead to substantial complications, we can still get recovery guarantees over here, right? So if now Y comes from this particular model, so you have phi of X W1 star, where W1 star is the ground truth, phi of Z W star 2 star transpose. If the ground truth comes from there, Then if, again, some assumptions, we do have assumptions where X and Z for our normal IID, and we are only able to analyze the sigmoid case. Then if omega is uniformly sampled, then, and the initialization, so this is the case where initialization, we assume that we are close enough. And the way the proof technique works is it actually uses similar techniques as the 2017 paper. And we show that the function is locally strongly convex around the ground truth. So this is a small step in giving recovery guarantees, but still, the real challenging part is to see whether it can actually be extended to this particular, when you have multiple layers. And now, when you have multiple layers, these are methods that are actually used quite a bit in many problems in industry, actually. I think they have, DSSM model is one name. I've heard two tower networks, Siamese networks, different names, but many applications actually use this model. Let me see, how am I doing on time?
So we still have, I guess, half an hour left.
Half an hour. Okay, so maybe I'll just step it up a little bit, but because sure. Maybe I've been going a little too slow, thinking I had a lot of time. So the third challenge I'll talk about is positive unlabeled learning. And in this case, let me go back to the problem that I worked on with the biologists at UT. So this was actually with my colleague and good friend, Edward Marcotte. And the problem is to predict genes which might be associated with a particular disease. So here, so what Edward Marcotte worked, I think, for about a decade, is to try and get functional gene networks. So that means if there is an edge between a solid edge over here denotes a functional relationship, for example, between the gene AVP and AVPR2, right? And so the biologists worked really hard to get this functional gene network from various sources. And then the second part of the data is in known associations between genes and diseases. So for example, over here, dotted black line is a known association between diabetes and the genes AVPR2 and diabetes and the gene AVP. And then you have similar data for other diseases and other species, right? So, mice, plants, and then we also had phenotypes and yeast, and I think there were a total of 6 species. And so one problem that Edward Marcotte posed to me was, hey, can we actually develop a machine learning method to make predictions in a ranked order as to what gene might be associated with a given disease, rank them, and then, of course, the biologists may go into the wet lab and perform experiments to confirm or not confirm the hypothesis that this gene might be related to this disease. So this is, for example, for example, with this, diabetes, this dotted green line indicates that there may be a there may be a relationship between that gene and the disease. So this is, given a disease, I want to predict which of these genes is associated with this. This is a multi-output prediction problem. And then as we started working on this problem, my students, Naga, and at that time, Ambush Tiwari was working with us. We asked them, hey, can you actually provide negative examples? Because it would be really nice to have negative examples. And we kept on asking them, and the biologists kept on kind of differing. And then finally they said, no, we cannot say that a particular gene is not related to a disease. So this is an example where we only have positive relationships, but no negative relationships. So going on with sort of the previous pictures, I have, again, lots of missing values, but now I only have once in the target. There's nothing else. So, so this is like, you can think of it as a different class of problems. In supervised learning, typically you have positive, negatives. Semi-supervised, you have positives and negatives and unlabeled. And in positive unlabeled, you only have positives, but you also have a lot of unlabeled data. Okay, so, and this is pictorially how we can try and model it, that the underlying distribution has positives and negatives. And many of these cases, the number of negatives might actually be much, much, much more than the number of positives. But the data that you see is such that you only get like an observation of this, where you see some positives, but you actually don't see any negatives, right? So any positive that you get, for example, in the biology application, has very high confidence that that observation is correct. And so how can I, if I try to model this problem using sort of the kind of methods that I've talked about, for example, inductive matrix completion, then, it doesn't, if you just look at this particular problem and all the Yij's are only ones, you can very quickly see that the degenerate solution might be all ones, right? And so what people have observed even before in practice is that what one can, so this is a technique used in this 2010 paper, which we call biased matrix completion, which is that you can actually give a high weight to the known observations. And then you can just kind of say that with lower confidence, all the remaining values are negative, right? And then you can solve this problem. And what people found is that these generally gave better results for the kinds of problems that they were looking at. So what we did, was to show that you can actually provide recovery guarantees for these biased formulation. I'm not going to go into detail over here, but then these methods actually perform quite well in practice, where we use sort of a inductive matrix completion, but a positive unlabeled version of this problem. So, so this was a paper published in Bioinformatics, where we are able to now get the features for diseases using gene networks, phenotypes, microarrays, and then similarly get features for diseases using, there's a lot of text data on these diseases, and then there is comorbidity data for sort of co-occurrence of various diseases. So somehow get latent variables, latent factors, and get them into features, get this into features over here, and get this model. And this ended up outperforming all the other methods. So this was a multi-year project with biologists. There were a couple of publications earlier before this one that I mentioned, where we were getting decent results, but when we use inductive matrix completion, the results were actually much better than mainly because I think we were able to incorporate all these different kinds of features.
So we have a question from the audience. Question is from Devda Dubashi. So question is, seems like the alpha will be very crucial here. Can you comment on the sensitivity to alpha?
Yeah, so in the paper, we actually had a couple of models for how this how we observe. So we had so alpha, you can think of this as like a problem of learning with noisy labels, and you can have like a probability where the noise for the positive class is one way, or let's say rho plus, and the noise for the negative class is rho minus. And you can actually, in the theory, we can actually relate alpha to those values, right? And so it really kind of depends upon the underlying data set a little bit, right? It's not just universal for every data set, but it depends on the data set and some of the things that I mentioned before as to what I said, for example, is that there are typically very few positive labels associated with an input, but a large number of negatives. And so there's alpha intimately depends upon knowing that. So you can actually come up with an alpha if you knew these, and then you can try and estimate that also.
All right, thank you.
Sure. Okay, so now let me turn to the last part of the talk, right, which is going to be pretty geared towards improving in practice the performance of these methods. So one kind of drawback over here is, for example, let me just see a slide. Maybe I'm going too far. Let me not do that. But one of the problems is that when we are given an input, the number of outputs may be in the millions, right? So even though we have a model like inductive matrix completion, the problem generally does not come that we are given features of both the inputs and the outputs, and we need to predict for just that pair. Typically, the problem is I'm given an input, there are features on the output, give me the top K, right? So one technique that one can use is the previous techniques that I've talked about, coupled with some quicker way of doing that inner product computation or estimation of the top K values. So there is work in sort of, MIPS, maximum inner product score, and so on. So one can go in that direction, right? But generally, the performance of those methods is still not that good. So I will now talk about this alternate framework that we have, which is really geared towards scaling up these methods in practice. Okay? So this is what I call the PECOS framework, prediction for enormous and correlated output spaces. Okay, so just to kind of reiterate what I just said, suppose you are trying to do product search. You are given an input query, and you have to find a product from, let's say, millions of products, right? It's not that you're given a query product pair, but given a query, you have to find a product from about 1 million. Similarly, you are given a product, you may want to try and predict the queries. And in related searches, given a query, you might want to try and predict the other searches. So one common task over here is, these are different problems, but they are a common task. Given an input, right, do this kind of extreme multi-label ranking, or essentially provide predictions for enormous and correlated output spaces. Okay, and in this case, I will consider text inputs only, right, because text inputs are what is applicable in the problems that I've shown above. So now again, let me just remind you of the setting. I have millions of outputs or labels. Most values are missing. It is a PU learning problem. There is correlation between labels, but I want to do training efficiently, and I want to try and do real-time inference. So if I'm, for example, trying to design, let's say, product search, I need to be responsive to the user. So the question is, how can I design practical methods such that I can enable this kind of real-time inference? So the rest of my talk will be, have a more sort of experimental flavor. And so let's see how we can try and do that. And one of the issues again that arises is that in practice, the outputs are not the kinds that we talked about in the theorems, right? Where we kind of have somewhat uniform sampling. We do have like a long tail of outputs, and that's because there is a paucity of training data for these outputs, right? And like the problem with PU learning, we only have positive training examples available. And one of the things that we need to do is, in the biased matrix depletion case, we just kind of punted and said, hey, we'll just give a 1 minus alpha weight to all the others. But then the optimization problem is huge, especially if you have, different loss functions. And so one of the things that you need to do is you need to try and have some empirical way of trying to identify the negatives, a small number of negatives due to this enormous output space. So I'll talk about computationally efficient schemes for doing training and inference. I'll talk about this PECOS framework that allows us to transfer, essentially kind of exploit correlation to transfer the training data from head to tail outputs and efficiently infer strong negatives. So before I sort of go into detail, the examples that I gave were a little bit suggestive. So in the design of, let's say, modern search engines typically proceed in 3 ways, right? So the problem is, let's look at web search, right? Problem is, given an input, find a relevant web document or a web page, okay? So typical search engines might construct like an inverted index. So they first do an indexing step to organize their documents, right? Which are the outputs that we are considering. Then most typical search engines have a phase of matching where they very quickly go from millions of outputs to a few thousands. And then they do a much more expensive ranking of these few thousand pages. So there is this 3-step framework that is employed in this information retrieval literature or the search engine literature. So when we were thinking about our problems, we said, okay, can we look at that same kind of 3-phase framework for our problems? Okay, so that's what PECOS does. It organizes this machine learning problem into 3 stages. In the first stage, we do a semantic indexing of the outputs or the labels. This can be through either clustering or through some data structure such as a nearest neighbor data structure. So this parallels the lexical indexing step that's done in search engines. So here we call it semantic because it is somehow capturing higher order information between the outputs. Then we do a machine learned matching step. And the goal of semantic indexing is essentially so that we can go at inference time from trying to have to analyze all the outputs to just looking at a small subset of the total number of labels or outputs. And then we can do a more expensive machine learned ranking step at the end. So let me kind of go into each of these a little bit more into detail. So, first thing is you can construct semantic representations for the outputs. When the outputs are text features, then I can do things like use transformer models such as BERT or Roberta to actually get embeddings for inputs and correspondingly the outputs through this training data. And once I have these semantic representations, then I can think about doing, for example, clustering or hierarchical, and maybe even organize the outputs in a hierarchical manner or arrange them in an approximate nearest neighbor graph. So this essentially organizes all the possible outputs. And the goal of this step is to enable us to go from, given an input, go from millions of candidate possibilities to a few thousand candidates. Okay? And the question is now, how do you go from the million possibilities to a few thousand candidates? So for example, if we do indexing using hierarchical clustering, then the matching problem itself, so now the matching problem is given an input, instead of finding each individual label, you try and find, or output, find each individual label cluster of labels or cluster of outputs. So now if you think about it, that problem itself is this kind of extreme multi-label problem itself. And now if we have the indexing in a hierarchy, then we can actually do this matching in a hierarchical manner. So this is what this picture indicates, okay? And in practice, we basically build, so think of now the outputs as being organized in a hierarchical tree, and then associated with each node, for example, the root, there is a classifier of whether to go left or right for a given input. And they can go both ways, okay? So then we can build these matchers so that we can very quickly go from the root to the bottom of the tree, which is going to be itself a cluster of labels. And then once you get to the cluster of labels, these are now the candidates, the few thousand candidates that need to be ranked. So we are able to then, again, use a little bit more. We have many fewer candidates, so we can spend more time to do some sort of ranking, but it still has to be done efficiently if we want to achieve millisecond latencies. So, one question is that when, for example, there are text inputs, can we do something, exploit the latest advances in techniques like, these deep pre-trained transformers, for example, BERT models. And, when we did experiments first, and we actually did not see much gain for example, the Wikipedia prediction problem of using BERT embeddings, right? So the question is how can you use them more profitably, because they should be able to capture, better higher order semantic information. So then we realized that if we add like a task specific linear layer on the top, we can actually get a trainable vectorizer for the problem that we have at hand. And using this trainable vectorizer, we can get a matcher. Remember the matcher, or deep learned matcher, which goes from the input to the, to not the outputs, right? It actually is going to a cluster of the outputs, just going directly. So if I look over here, our trainable vectorizer has k columns. K is not the same as L. That'll just be too expensive, right? Because that'll put us back in the same picture as having a giant softmax. So we actually use the indexing structure to, so that the BERT model, the trainable BERT model actually goes from input to a clusters of outputs. And then after we get clusters of outputs, then we can do a final ranking step like before. Okay. So I'm sorry, I'm going through it pretty clearly. This actually work is presented in a KDD paper, and I believe the KDD paper conference is happening this week. So just a little bit more detail, for, we can have different deep text vectorizers, BERT, XLNet, Roberta, and we are able to get a trainable deep vectorizer using this coefficient matrix W. And just to sort of give you an idea of the experimental results, we are now able to get kind of state-of-the-art experimental results for for various problems. So this is a publicly available data set that has 13,000 labels, so somewhat of a toy problem. X transformer, sorry, I should have mentioned it, this deep trainable vectorizer we refer to as X transformer. And then when we do this XR linear model, it's basically a recursive linear model, which has, it actually, I think, does hinge loss classification at each intermediate node of this hierarchical tree. So just to kind of, there's no deep learning involved in XR linear. There is definitely a lot of deep learning involved in X transformer, and you do see the benefits, right? So here I've given the traditional metrics used in this literature, which is precision at K. So K is 1, 3, and 5. And you can see that there is some improvement, both in precision and recall. And like I mentioned, this is a paper that we're presenting this week. And in comparison, I've given some techniques that are out there for doing multi-class prediction based on fast text using softmax. Softmax gets too expensive for very large softmax outputs. So there is hierarchical softmax. Hierarchical softmax is faster, but you can see that it does lead to some decrease in performance. But like I said, this is a small data set on the wiki 500K data set that I had been showing to you. The deep learning model does give a pretty significant gain in terms of these metrics of precision and recall over XR linear. And there's also another paper called Attention XML. So our results are either about the same as Attention XML or slightly better. So, and this is the state of the art for these extreme multi-label problems. Now, in terms of precision recall, the BERT models are better, but I guess just a little bit of word of caution that sometimes you might be comparing, apples and oranges. So even though they are results on the same data set, the training time can actually be much, much larger, right? So for XR linear, our software, which is pretty efficient, can actually do this training in 17 minutes, whereas for the BERT models, it's multiple days. And that's the additional expense you have for obtaining this additional precision, okay? And also just to emphasize that, the linear model, the results that I'm presenting are on a CPU machine with 16 CPUs, whereas the BERT-based models are on an 8 GPU machine. And the 8 GPU machine is, I think, about 10 or 20 times as costly per hour as the 16 CPU machine. And similarly, on this larger data set, Wiki 500K, you do get a substantial bump in precision using these BERT models, these latest deep learning models. But, in XR linear, you can train, during the workday, whereas here it has to be about 2 weeks, okay? And of course, so that what I'm kind of hinting at is that the practitioner needs to really analyze the cost benefit trade-off as to what method they should use. And of course that can change, with changing hardware and changing models. If you, for example, can get more efficient BERT models and so on, this cost benefit trade-off can change. So one of the things that I think I alluded to was that the typical problem is, so I think I only have about 5 more minutes. Hopefully I'm not, I think that should be enough. So, the inference time is generally going to be linear, right? So suppose I'm given an input, I have capital L labels. If I use models such as inductive matrix completion, then, and I, just do a brute force search, then it'll be order L, the time to actually make the prediction or to do inference. And like I said, you can use other techniques like MIPS and or data structures like that do approximate k nearest neighbor. The model that I have proposed as part of this PECOS kind of does this intrinsically, right? So it organizes the data in this hierarchical, or the labels in this hierarchical tree. And because of that, we are actually able to do the inference in logarithmic time, okay? Time which is logarithmic in the size of the output space. So essentially what we can do is we can do a beam search starting from the, so take an input, start from the root, and then have a beam size of B, and then you go along and basically do this classification at each step, and each of the classifiers outputs some score, and you do beam search according to those scores. So again, like I'm skipping a lot of details, but the details are in a paper that we are writing. These are the enhancements that we've had to make to achieve the results that I'm showing now, right? So if you want to try and get prediction time in milliseconds, right, then this is one way of having done these, or to do these optimizations. So these results over here, let's just concentrate on the Wiki 500K data set. So Parabel is another implementation of somewhat similar idea, but the inference is much slower. So with XR linear, if I've just given the input in a vector form, we can do the inference in 20 milliseconds, right? Which can basically satisfy the needs of many real-time systems, okay? And of course, in practice, you are given text inputs, and fast text does it internally. So over here, we are able to do it in 35 seconds. That's going from the text input to the label. And then X transformer has higher latency, but you have to realize it also uses, this is not an apples to apples comparison, because this is using the 8 GPU machine, and this is using the 1 CPU machine. And just to point out, that fast text is very fast, especially the hierarchical softmax. But if you go back and look at the quality of results, hierarchical softmax is really poor in terms of performance. And here we had both softmax and hierarchical softmax, but training softmax is actually very hard or it takes too much time. So we actually had to stop that training. So even though we give the inference time, it's actually not a very good model over here that gives high precision. Okay, so the last part of my talk was more about practice, but just to recap, I talked about sort of multi-output prediction problems. They really abound in practice. So I outlined the challenges and gave various solutions. So for example, the first 3 bullets over here, we are able to develop also some theory, but many times, there is a gap in theory and practice. We saw that already in the inductive, nonlinear inductive matrix completion setting, where the theory that is developed so far is only for one hidden layer. But in practice, people use multiple hidden layers. And similarly over here, we have a method, and that method, of course, performs quite well in practice, but we haven't even tried to analyze that. There's a reason why. So future work, it's something that I'm actually actively working on, is to do more efficient neural network training and inference, try to do end-to-end training, because with the clustering, things are somewhat fixed. And one of the reasons of calling this project prediction is, so this prediction for enormous and correlated output spaces is that many times you don't just have a supervised learning problem in these settings, and you may want to try and extend to contextual bandits and or reinforcement learning. So we are trying to use this kind of framework where we can extend contextual bandit practice and theory to when you have an extremely large number of, let's say, arms or action spaces. So in conclusion, I would just like to really thank each of my collaborators. This work wouldn't have been possible without them. Wei Cheng is a recent graduate from CMU. He worked with Yiming Yang as his PhD advisor. He's an expert in NLP. Chojo Ishii is an ex-student of mine. He's now a professor at UCLA. Pratik Jain, I think it all started when I started visiting Microsoft Research back in 2012 or 13. He's an ex-student of mine, of course, very well known in this field, and pleasure to work with. Naga, who's an ex-student of mine and is now in Microsoft Research. CC is now in Google Research. Shangfu is also someone who I did a lot of the early work on multi-output prediction problems. Jiang is a recent graduate and is working on the BERT and transformer modeling. Kaizong graduated a couple of years ago and was really instrumental in developing some of the theory that work that Pratik and I had started to do, and extended it to neural networks. So I am happy to take questions, but I am leaving you with some of the references to the papers that I've mentioned and some other papers. Of course, if you go into each one of these papers, there is a large bibliography with each one of them. Okay, well, thank you for listening.
Right, let's thank Inderjit for the great talk. So we do have one question in the chat box. So the question is, for inference in PECOS, are we using GPU for the X transformer?
Yes. So maybe I shouldn't have stopped sharing my screen, actually.
Sure.
I was too hasty. Okay, so let me go back. Yes, the answer is yes. So for example, the X transformer timings are the average inference time, right? And so if you look over here, this is an 8 GPU machine. So the comparison is really not fair between these numbers and these numbers. I just put it there for, a sense as to what the latency is like. And if you see, the number is not that different between 13K and 500K. And that's because of the BERT training that's involved. So, yeah, so the answer is yes, it is on a GPU.
Thank you. And let me ask a question while people are thinking of their questions. In your earlier parts of the talk where you talk about recovery guarantees for cases where you have missing labels, I'm wondering if that could be extended to multi-dimensional scale with perhaps censored distance observations.
So sorry, could you, I guess I didn't understand your question. Could you repeat it?
Yeah, so I guess, for the recovery guarantees where you have missing labels, right? I was wondering if the analysis or perhaps the techniques could be extended to multidimensional scaling where perhaps the distance observations are censored.
Oh, I see. So you're saying that, MDS.
Right.
Yeah, I actually had thought about that problem, but it's been a long time ago. And I thought that there was some literature in, multidimensional scaling and thinking of it as modeling it similarly to matrix completion. But in some sense, that is slightly different from the work that I talked about, because in this case, in typical multidimensional scaling, you're given a matrix, right? And you want to try and embed it in a lower dimensional space, right? And in our case, most of the methods that I talked about are inductive. That means you get a new input described by their features, and then you want to take you want to make a prediction. So I mean, I actually haven't heard it gives me an idea, but I haven't heard of an inductive version of that problem. But it does make sense, right? So suppose you have given an n by n matrix among observations, but they also have features, right? And now a new object comes along for which you don't have any data, or you don't have its embedding. You don't know the distance to the neighbors, and can you, and then these methods, yes, they can be extended.
Right. Yeah, so the reason why I was asking was because, in multidimensional scaling, people are usually assuming that all the distant observations are given, right? But then you can think of many cases when, you don't actually have a lot of those distance observations, and that it might be possible to use the techniques you have, right, for that setting.
Exactly.
Cool. And then maybe let me ask another question. So do you see perhaps, an extension of optimal transport for this problem where, for example, you want to see, say, something where, perhaps one instance is only associated with, at most K labels. Do you think, that's would be perhaps useful in applications, and, can you sort of think of any extensions of your approaches to that setting?
So, I haven't really thought about that problem, but I guess maybe I'll ask you some clarification. So yes, I mean, over here, we can assume that one input is associated with K labels. Where did the optimal transport come in?
I guess I was just thinking of the doubly stochastic constraint, right? An optimal transport problem. So usually you would say, every row and column would sum up to one, right? But then you can think of.
I see. Yes. And you're actually right, because in a way you're kind of, yes. Yeah. Okay. That's a great question. I hadn't thought about it, but typically, you don't just need to know, what things are relevant. You actually need to output them in an order, a ranked order.
Yes.
Right. And you can think of those as maybe the probability of associating that. So I can definitely think of this as like for example, row stochastic. And I can now start saying that, if you have, because sometimes one of the things that, the input and output can actually be interchanged in these problems.
Yes.
In the setting that I'm talking about, right? So in that case, yes, maybe a doubly stochastic setting would make sense. And then, I think it'll be really interesting to see if ideas from optimal transport can actually be
Right.
be employed. I have not thought about it. You're the first person bringing that to my mind. So thank you for
Okay.
doing that. Yeah.
All right. Thank you. Are there any other questions from the audience? Perhaps I will ask about, I guess a high level question. So I guess in deep learning, there's always this non-identifiability issue, right? And perhaps classical, frameworks, right, where we always talk about recovery, right, might not be the most
Sure.
relevant. I was wondering if you have any thoughts on, what are sort of the relaxed notions that people can usually consider, right, in the deep learning context.
Yeah, I mean, you can try and look at the, generalization bounds and consistency guarantees.
Yes. I guess in the deep, I guess.
I think for a lot of these problems that I talked about, it should be possible to get them. For the nonlinear inductive matrix completion problem, also I think it should be possible. So, yeah, you're right that and those actually may make more sense in the settings that we are in, right? Because we may not actually consider, we may not be interested in exact recovery, but we are more interested in, like, how does the accuracy of the methods change as you get more and more data and so on. Yeah, it's just that, I haven't looked at it, but I'm sure other people have or will look at it.
Yes, thank you. So we have a question from Harsh. The question is, how does matrix completion compare with extreme classification loss functions? So I guess done by Manik Verma at MSR.
Yeah. So one of the methods that I talked about is Parabel, which was actually developed by Manik Verma's group. And so and that was the last part of the talk when I was talking about PECOS, where we really need to scale to, in some sense, industrial size applications. So the earlier work that I talked about was, I mean, it is meant for, extreme multi-level learning, right? And so the 2014 paper I wrote with Pratik was on extreme multi-level learning. And at that time, it was state of the art, right? But state of the art has advanced considerably since then. So now, we've had to modify the methods. So the problem with matrix completion is that it actually, low rank matrix completion is that in real life, what tends to happen is that this low rank structure is not enough. Or the low rank structure, because many of these labels are tail labels, they have very few observations and they may actually be outliers, right? So modeling as the whole globally as low rank may not work. Now you could model locally as low rank. So that is, some technique that we try to do it in the context of PECOS, but so far it hasn't yielded better results than what I showed you.
Thank you. And perhaps another question regarding PECOS. Have you thought about the streaming case and, I guess there's sort of, two challenges I see. One is the banded feedback, right, which we sort of alluded to in the last part of the talk, but then there's also the question of how do you actually, design sort of a data structure that would allow you to do, fast inference, right?
Okay, good question. And actually, there's a little bit of a disconnect between the title that I have. The title is the vision that I have. So PECOS is prediction for enormous and correlated output spaces. Now, if you look at the method, it is actually correlated outputs, okay?
Right.
Typically, the output space would have some structure to it. And where, for example, if you do clustering, you're not just doing clustering on the set of outputs, but you're doing some decomposition of the space itself. And what that means is that if I now am given a new label or output, I should have some way of figuring out what part of the space it belongs to, right? So, and so by, and then if I get something which is new, then I have made a discovery that the space is not captured by what I'm doing right now. So yeah, it is possible to get kind of streaming generalizations. And, you know, one of the things you could do is you could actually kind of do streaming hierarchical clustering and then find, I'm just thinking out aloud, and then kind of find a way to, you know, have a very quick update of these parameters. Or maybe just use the existing. Oh yeah, so actually, yeah. So I'm actually working on a scheme with a couple of people where we get away from this notion of a fixed label set and really think about, or an output set, and think about output space. And I think the streaming setting will make much more. It'll be much more intuitive to handle the streaming setting in that context.
Mm-hmm. Right, thank you. All right, are there any other questions? Okay, if there are no more questions, that concludes today's seminar. Let's thank Inderjit again for the very interesting talk.
Okay, well, thank you for having me.